This is the solar panel coating evaluation project. The group members are Austin Cords, Megan Gerard, Dan Jones, Paul Rockowitz, Josh Robinson, Kelly Schultz, and Jacob Weeses. Our sponsor for this project is Grand Valley State University. Our sponsor contact is Dr. Zhao, and our advisor is Dr. Peng. This project encompassed multiple tasks with the final objective of being able to evaluate the performance of 3 selected solar panel coatings. This evaluation was based on in-lab and field tests. Selected coatings were tested for durability and transmission through various tests. The in-lab testing involved the falling sand test, force sand test, and light simulator test, while the field testing involved placement of the panels in 3 different environments, and our goal was to have the fixtures last at least 5 years. The in-lab testing, we followed published standards. In the case of the falling sand apparatus, we followed DIN 52348 standards, with the most important specifications being the diameter of the orifice, guide tube inner diameter, and impact velocity. For the force sand apparatus, we followed the MIL STD 810G standards, with the most important specifications being the air velocity and the sand concentration. A single fixture was designed to hold both the forced and falling sand devices. It was constructed of wood and it is height adjustable. To ensure the repeatability of our cleaning methods, a CNC air/brush device was used, and a mounting plate was designed to make the brush and air nozzle easily interchangeable.
Our light simulator fixture design can be seen here. The frame was constructed from wood using 2x4 planks. A 120 watt to 240 watt light bulb was used to simulate solar light. It was placed in the wood frame by a 3D printed connection to a PVC tube which housed an extension cord to power the light. This tube gave the light simulator height adjustability, which was used to test the light intensity. Black fabric was draped over the entire structure to ensure no other light source was interfering during the testing. A solar panel could be placed in the fixture under the light, and the voltage and current from the panel could be read using a DMM. For each coating, 3 samples of glass were used. These coatings included a control, nanotech, solar shield, and glass parency. These 3 samples of glass per coating each represented a trial which would then follow this in-lab procedure. An initial light simulator test would be performed first without any abrasion or damage to the glass sample. Then a falling or forced sand test was performed based on the mentioned specifications. For the falling sand test, a set amount of sand was placed in a funnel and released onto the glass sample. This test was complete once all the sand in the funnel had gone through the system. For the forced sand test, sand was constantly supplied into the funnel for 1.5 hours. As sand fell through the funnel, it was sent into a 1-inch PVC tube connected to an air supply. This gave the sand an exiting velocity of 18 meters per second. The sand then hit the glass sample at 45 degrees. After either test, a second light simulator test was performed. This was followed by a CNC test where 1 brush stroke would clean all the sand remaining on the panel. A final light simulator test was performed to view the effects of the sand after the sample had been cleaned. Our completed in-lab fixtures can be seen here. On the left is our light simulator fixture, where the black fabric can now be seen. This fabric also closes over the open section shown as well. Next, the CNC fixture is shown. A video in a later slide will show the device doing a brush stroke over a sample of glass. Next, the forced sand and falling sand fixture. A section of glass with a coating was placed on a stand over a box to collect falling sand. This stand was placed at 45 degrees for the forced sand test and flat for the falling sand test. This video shows the working CNC fixture. This video shows the working forced sand fixture. Notice the sand is coming out of the PVC tube and landing on the glass panel placed below. In this video, the falling sand test and fixture can be seen.
For field testing, groups of panels were placed in 3 separate locations for an ongoing period of time to evaluate their performances at each location. Each group consisted of 4 panels, a control panel, and 1 for each coating type that was evaluated. The data stored from the panels was collected weekly, and the electrical equipment was protected using a cooler. The groups of panels were placed at the roof of the Keller Engineering Building, Holland State Park, and the Sustainable Agriculture Project on the Allendale campus. For the field testing, the output voltage and current from each set of panels is recorded once per hour in 11-minute intervals. This means that every 11 minutes, the solar panel that the e-logger recorded would switch to a different solar panel. These outputs had to be recorded within 10% value reading from a DMM. To ensure this specification was met, each group of solar panels was tested with a DMM and compared to the recordings on the e-log device. The e-log device is specifically made for recording solar panel output through a solar charge controller. The solar charge controller collects data from each of the 4 panels, the battery, and the load. The e-log then records the voltage, current, and power outputs. As seen in the schematic, the solar charge controller is connected to the panels through the relay modules that switch between the panels. The e-logger is then connected using the RJ45 cable for data transfer. This data transfer happens every 11 minutes as pre-programmed in the e-logger factory settings. The e-logger is able to store about 4 months of data or 20,000 data points and can be exported into an Excel file using the e-log program. The Arduino module is powered using the solar charge controller load. The Arduino is used to control the relay module and store the time, date, and panel numbers. To ensure the timestamp that the e-logger stores the data from the panels is correct, there is an external RTC module connected to the Arduino that stores the time, date, and panel numbers into an external SD card every time the relay switches to a different solar panel. The data stored on the SD card is stored in a text file and compared to the date stamps collected from the e-log device. The 6-channel relay module uses 4 channels, 1 connected to each solar panel, and is controlled using the Arduino. The signal from the solar panel goes into the common port. Then, using the normally open port of the relay module, the solar panel signals are connected to the charge controller. Using the normally open port of the relay modules allows for the channels to be controlled by the Arduino so that only 1 channel is connected at a time. When a channel signal is opened, it stays open for about 11 minutes. While the signal is connected, the e-logger records the data from the charge controller. The Arduino then signals for the relay module to disconnect the channel and connect the next solar panel.
This project occurred over 2 semesters. Design of the fixtures and development of the testing plans occurred throughout the first semester, and at the start of the second semester, building began. The field testing fixtures were prioritized to maximize available data for evaluation of solar panel coating performance in the field, and in-lab testing began towards the midway point of the spring-summer semester. Our budget was just over $3,500, and we spent a little over $3,300. Cost was pretty tight due to the desire to include a 3rd coating for evaluation. This drove up cost compared to the initial proposal, largely due to costs of the additional outdoor fixtures and solar panels required. Some of the challenges faced during this project included designing testing procedures and fixtures to meet specifications. The forced sand testing fixture in particular required several iterations after initial testing to meet requirements and ensure consistency. There was also limited material availability for the forced and falling sand tests that had to be worked around. And some of the tests were on the magnitude of hours, so timing in order to perform all of the testing required was a bit of a challenge. In the end, fixtures were successfully designed and built to allow for testing of solar panel coating performance, and groups of solar panels were deployed in 3 locations, and data has been collected weekly for the last 3 months from them.